All right, so starting chapter 3, we have a couple of things to look at before we get into exponential functions. But because we're going to be looking at exponential functions, I need to remind you about just basic exponent rules. This will come into play as we simplify some expressions. So remember that when you're raising a power to a power, that you multiply your exponents. So x to the a raised to the b power is x to the a times b. If you are multiplying x to the a times x to the b, that is x to the a plus b. You add your exponents. Note that the base number has to be the same. It's not x to the a times y to the b. They both have to be x's. Same thing here. If we're subtracting the same base number with different exponents, or if we're dividing them, we can subtract our exponents, a minus b. And x to the negative a, it's because of this. If you get x to the negative a, that would become 1 over x to the a. And the reason for that is because, let's do one more here actually. X to the 0 is equal to 1. And why is that? Because think about this. If you're getting 0 in your exponent, it means you subtracted the same number. So in order to subtract the same number, I would have had to have like x to the a over x to the a, right? So that it becomes x to the a minus a. And x to the a divided by x to the a would divide out to 1. If you're getting a negative exponent, it means you could have x to the 0 over x to the a, so that would subtract out to negative a. Also, one more thing. If you have an if you have a negative exponent in the denominator already, that's still the reciprocal of a number. So instead of the reciprocal, instead of going down to the denominator, this would get sent up to the numerator, and you would just have x to the a over 1, or just x to the a. All right. Geometric sequences. We talked about arithmetic sequences in chapter 1. So now geometric is a sequence where the ratios of consecutive terms is the same or is constant. So for example, this is a geometric sequence. You maybe can see the pattern without having to calculate, but to calculate or to check if it's not obvious looking at it, divide consecutive terms. It has to be the next term divided by the previous term. That gives me 2. 8 divided by 4 also gives me 2. 16 divided by 8 is 2. And 32 divided by 16 is 2. So the fact that I keep getting 2 when I divide, that's called a common ratio. Remember, with arithmetic sequences, we called it a common difference. So now it's a common ratio. We use the lowercase r to represent that. And in this case, the common ratio would be 2. How do you calculate terms in a geometric sequence? So maybe they give you this sequence and they say, okay, find the 100th term. You could just keep multiplying 2 until you get out to 100, or you could use this formula. So the nth term will be the first term times the common ratio times n minus 1, or to the n minus 1. And so let's check that with this one. So in general, I should be able to get any term by taking the first term 2, multiplying it by the common ratio, which was 2, to the n minus 1. So if we check that, this is the first term, the second term, the third term, fourth, and fifth. So let's just check, does this work for the fifth term? So if I want to find the fifth term, I get 2 times 2 to the fourth. Is 2 times 2 to the fourth 32? Yes. Now, this could be the nth term, or you have to be prepared to work with exponent rules for the AP test. So what if you don't see this in your list of multiple choices? Well, they might have used a little exponent magic here. If I was subtracting 2 to the n minus 1, that means I could say that was 2 to the n divided by 2 to the first, right? I'm using this exponent rule right here. If I had subtraction, we're going backwards and saying, oh, that could be x to the a over x to the b. Okay, and then what is that? Well, 2 times 2 to the n divided by 2, those 2's can cancel out. So it could be that a to the n is just equal to 2 to the n. Check that for these terms. Does that still work? Is the first term 2 to the first? Is the second term 2 squared? Is the third term 2 to the third? Yeah, that works too. So this is probably what we would have in our multiple choices rather than this, but they are both correct. We use sequences in BC calculus too, and as long as the sequence, the formula that you write down, generates all the provided terms correctly, then that's an equivalent sequence. What if you're not given the first term? So more generally, if you're not given the first term, any term you are given, like we'll just call it the kth term, it would be a term that you desire is generated by a term you know times r raised to the n minus k. This is just the difference between these two terms. Are they 4 terms apart? Are they 10 terms apart? Whatever. We'll look at this in a couple of examples. So a lot of what we will be doing for the AP test is deciding, is this sequence or is this table arithmetic or geometric? Arithmetic if there's a common difference, geometric if there's a common ratio. So answer that and then find the next 3 terms. Okay, so I'm looking at this. If it were a common difference, if I subtract, I get 10. But then if I subtract the next one, I don't get 10, I get 30. So it's not arithmetic. Geometric should just be I can divide consecutive terms and I keep getting the same ratio. 45 divided by 15 is 3. 135 divided by 45 is also 3. So yes, this is geometric. So I've got that answer. And then what are the next 3 terms? So because the common ratio is 3, I should just multiply 3 to get the next set of terms. So I'm going to have to do this on my paper here, which is good practice. 3 times 5 is 15. 3 times 3 is 9, plus 1 is 10. 3 times 1 is 3, plus 1 is 4. So the next term is 405. I have to multiply that by 3. 3 times 5 is 15. 3 times 0 is 0, plus 1. 3 times 4 is 12. And last time, multiply this by 3. 3 times 5 is 15. 3 times 1 is 3, plus 1 is 4. 3 times 2 is 6. 3 times 1 is 3. So 3,645. All right, so those are the next 3 terms. What about this one? I'm not noticing a common difference. 8 minus 16 minus negative 16 is 24. Negative 4 minus 8 is not 24. So let's check for geometric again. 8 divided by negative 16 would reduce to negative 1/2. Negative 4 divided by 8 would reduce to negative 1/2. And 2 divided by negative 4 would also reduce to negative 1/2. So this is another geometric. And the common ratio is negative 1/2. So to get the next 3 terms, we should keep multiplying by negative 1/2. So 2 times negative 1/2 is negative 1. Negative 1 times negative 1/2 is positive 1/2. And positive 1/2 times negative 1/2 is negative 1/4. So those are the next 3 terms. All right, what about number 3? So 20, 13. So if you try geometric, 13 divided by 20 doesn't reduce. 6 divided by 13 is not the same as 13 over 20, so not geometric. If I subtract the next term minus the previous term, 13 minus 20 is negative 7. 6 minus 13 is negative 7. Negative 1 minus 6 is negative 7. So this one is arithmetic. And the common difference is negative 7. So that just means we should be subtracting 7 to get each term. So I don't think I have to show the work for that. Negative 1 minus 7 is negative 8. Negative 8 minus 7 is negative 15. Negative 15 minus 7 is negative 22. All right, the next example says write the nth term in the geometric sequence. So write the nth term means come up with the formula like we did up here. Like what is the formula to generate these terms? It's 5, then 5 times 3, then 15 times 3. So how do we come up with a formula that just lets us plug in values for n and generate these terms? So use the formula we know. We have the first term. We have a1. So we might as well use the first one that says the nth term is the first term times the common ratio raised to the n minus 1 power. All right, so we're not going to plug anything in for the a sub n. This is just our nth term is equal to, the first term is 5. What was the common ratio here? We did this before, but the common ratio is 15 over 5, which was 3. And you want to make sure that you get 3 each time you divide. 45 over 15 is 3. 135 over 45 is 3, so 3 to the n minus 1. Now, again, if you're just writing the sequence, maybe it's a free response question, then we could leave our answer like this. But if we need to simplify this so that we don't have negative exponents, or if we don't see our answer in the multiple choices, we need to work on it a bit. So remember, you can say 3 to the n minus 1 using my exponent rules could be written as 3 to the n divided by 3 to the 1. So instead of subtracting your exponents, you make it a division problem. And then you want to leave the 3 to the n, but 5 divided by 3 could be written as 5/3 times 3 to the n power, or just times 3 to the n. So this is another option for generating these terms. And you can check your work. Do you still get 5 for the first term? So if you plug in 1, 5/3 times 3 is 5. If you plug in 2, 5/3 times 9 gives you 5 times 3, and that does give you 15. So you can check your work here too. All right, what about this one? The fourth term of a geometric sequence is 125, so a sub 4 is 125, and the 10th term is this fraction, so a sub 10 is 125 over 64. Assume the terms are all positive, so we're not going to have to think about a negative r. So how do we figure out this one? To write the nth term, you need to know what r is equal to, and I don't know the first term, but I do have, and I can't just divide these because they're not consecutive terms. But remember, we have this general formula that says, okay, the 10th term could be the fourth term times r to the 10 minus 4. So let's start there. The 10th term is equal to the fourth term times r to the 10 minus 4. Let's sub in the numbers that we know. We know the 10th term is 125 over 64. We know the fourth term is 125. And this would be r to the 6th. We need to solve for r. So let's divide by 125 or multiply by 1 over 125. So 1/64 equals r to the 6th. I can get rid of a 6th power by taking the 6th root. Oops, I said 6, I wrote 3. By taking the 6th root of 1/64. Take the 6th root of both sides. I'm not going to put plus or minus because this says assumed terms are positive, so no plus or minus. What is the 6th root of 1 over 64? In other words, what number raised to the 6th power gives you 64 down here? That would be 2. So 1/2 is equal to r. And again, not plus or minus because it says positive. So I have r now. So if I want to write the nth term, I could say, well, the nth term is equal to, start at either the 4th or the 10th. I would start at the 4th term because it's not as ugly of a number. This is the 4th term times r to the n minus 4. Or you could say a sub n is equal to 125 over 64 times 1/2 to the n minus 10, because this was the 10th term. So I would go with this one. Okay. So what about exponential functions? So that was kind of geometric sequences, a quick little thing for our AP test. What about functions? We're going to be looking at working with exponentials. So you have an exponential function if the base is a real number greater than 0, not equal to 1, and the variable is the exponent. So f of x equals a to the x power. X has to be a real number. We won't be raising to imaginary exponents, for example. So let's just sketch a couple of graphs just by using a table of points. So if I want to think about f of x equals 2 to the x, 2 to the negative 2 is 1 over 2 squared, so 1/4. 2 to the negative 1 is 1/2. My pen working again. 1/2. Anything to the 0 is equal to 1. 2 to the first is equal to 2. And 2 to the second is equal to 4. So I believe you guys have a nice little graph on your paper, but I have not, excuse me, updated mine. Goodness. Okay, so when I plug in negative 2, I get 1/4. When I go to negative 1, I'm at 1/2, 0, 1, 1, 2, 2, 4. So exponential functions have this curve happening. If your base number is a number larger than 1, then you're going to get this shape of the graph, and how quickly it grows depends on what this base number is. The higher the base number, the faster the graph grows, or the steeper it will look. There's no way this graph could be 0, right? Because if you just keep plugging in more negative, like 2 to the negative 100th is going to be a very small fraction, but not exactly 0. So there is a horizontal asymptote. It's at y equals 0. And that's because the limit as x approaches negative infinity, so as we trace to the left of f of x, that's equal to 0. The left side of f of x approaches 0. All right, what if we have a base number that's a fraction? So when I raise 1/2 to the negative 2, that's going to be, flip that, 2 squared is 4. 1/2 to the negative 1, flip that, it's 2 to the first, so 2. Anything to the 0 is 1. 1/2 to the first is 1/2. 1/2 squared is 1/4. Again, you should have a little graph on your notes, but let me just generate one for mine. Sketch this. So -2, 4, -1, 2, 0, 1, 1, 1/2, 1, 1/4. So this has the same curvature, except it's going in the opposite direction. So we have another concave up graph, but it's a decreasing function. So there is a horizontal asymptote for this one. It's only on the right. So it's again at y equals 0, and that's because the limit as x approaches infinity of f of x, h of x for this one, is equal to 0. So that's because the right side of h of x approaches 0. So what are some nice points that we need to graph? You're welcome to do more than 2. Sometimes only plotting 2 kind of confuses people, but what am I grading? I am mostly just grading that you have the horizontal asymptote. It's originally y equals 0. This is all before transformations. Both of these graphs had a nice point at 0. They had a y-intercept of 1. And another easy point to plot is when you plug in 1 for the exponent, you get the base number, which is a. So you're welcome to plug in another point on either side of that, plug in -1, plug in 2, but this is all I'm really grading. We also need to know what these transformations look like. So we're going to be graphing some of these today. So remember, anytime you add or subtract outside of a function, that is a vertical translation. So what does that look like? It looks like adding or subtracting a number at the end of or out in front of the exponential term. If you have addition or subtraction in the exponent, that's where you get a horizontal translation. If we have a negative out in front of a function, so it's not in parentheses, it's just out in front, that would be an x-axis reflection, which is when you have x negative y. If you have a negative, in the exponent, that's your y-axis reflection because the negative is inside of the function that way. That's where the x's get negative and the y's stay the same. And then similarly with our dilations, if we have a number out in front of the function, so it's not in the exponent, it's out in front, that's a vertical dilation. And remember, with dilations, it's by a factor of c because every y value gets multiplied by c. And if we have a number being multiplied inside of the exponent, that's a horizontal dilation. Remember, the factor is not c, it's 1 over c, because every x gets divided by c, and the y stays the same. All right, so we're going to end with these 3 graphs here. So what are the nice points for the 4 to the x graph? 0, 1, and 1, 4. And there's a horizontal asymptote at 0. And then what has happened to this? So we have an x-axis reflection. And then after that, we're going to go left 2. So the x-axis reflection is x negative y. That makes this 0, -1, and 1, -4. It doesn't affect the horizontal asymptote. So I like drawing that in first. Each of these points need to go to the left 2. So 0, -1 goes left 2. 1, -4 goes left 2. And I draw my curve. For the next one, I've got this special case in here. factor out the negative so that you can really see what the horizontal shift is. So the nice points on the original 3 to the x graph are 0, 1, and 1, 3. Now, when I do my x-axis reflection, or my y-axis reflection, excuse me, that's negative xy. So that becomes 0, 1, negative 1, 3. And then I need to shift everything up 2. That does shift the horizontal asymptote. So if it was at 0, it's now going to come up to 2. Because if this exponential can never actually hit 0, but you're adding 2, that's going to be the minimum value. And then 0, 1 goes up 2. And negative 1, 3 goes, up 2 and left 1. And then negative 1, 3 goes left 1 and up 2. It's left 1 because we factored a negative out of our parentheses, so left 1 and up 2. Okay, final graph. So what's the 1/2 to the x? What are the nice points? 0, 1, and 1, 1/2. And then what's happening? We have a vertical dilation. Every y value gets multiplied by 2, and then we're going to go down 4. So let's do the dilation. So that becomes 0, 2, and 1, 1. Multiplying y equals 0 by 2 doesn't matter. When you shift down 4, that will move the y equals 0. So the horizontal asymptote is now at negative 4. The point that was at 0, 2 goes down 4. And the point that was at 1, 1 goes down 4. And I sketch this graph. Something like that. All right, so that finishes our work for today. Tomorrow we're going to talk about the number e and compound interest.